The first thing I want to let you know, I will extend the deadline. Yeah. So last time I said, I haven't changed. Yeah. So after our class tonight, I will make that change. All right. Yeah. So the homework assignment to be the deadline. I plan to, so the current deadline this Sunday, right? I give you one more week, okay? Yeah. This will be changed to May the 3rd, Sunday. So you have one more week. There is a good reason. First, we have plenty of time. Yeah. So we, before the final, we can afford one more week for this assignment, for this important assignment, right? Second, after this extension, we have more chances to explain more questions in this assignment. Today I will explain a few questions. So because after this week, next week, we have, the week between, right? Next week, we have Monday, Wednesday. I can use these two classes to explain a few more questions. So based on your, some students ask me questions through emails, so then I will explain in class to everybody, okay? More questions. So in this way, I think you can do better. All right, so that's our plan, okay? All right. So now, let me explain some of the questions. The first one, how to process the data. Based on your response, so I want to, clarify the meaning. All right. So in this case, we need to target the worst case, the number of comparisons for the worst case. But here, you cannot just apply our worst case formula directly, because our worst case formula, this is our worst case formula, under the condition, no information known, right? We do not have any known information, but here we have the given condition. So these two inequalities can help us reduce the number of comparisons. With the given information, we do not need to use, the maximum number of comparisons. So it is possible we can reduce a few number of comparisons. Right. So the question, how do you see that, right? How do you know the number of comparison you need, right? Right? So here, let me explain. Okay, all right. we apply the standard insertion sort. Yeah. We just apply. So this question is designed to check your understanding on the standard insertion sort. Apply the insertion sort. Right? Right. All right, yeah. But when we apply, so here, how to work on the given condition. Okay, yeah. You need to do the counting, right? So when we apply insertion sort, we have several insertion steps, right? Several insertion steps. And then we need to go through all those insertion steps. Okay, all right. So for example, we process the data in the given order. Okay, yeah. So the processing order we cannot change. Okay, all right. We use the natural order. This is natural order. The order for processing. We cannot change this order. Okay, so we have to follow this order to run our insertion steps. Okay, all right. Yeah. All right. But when you run insertion steps, sometimes you need to use the known information. Sometimes you have the freedom to make your decisions. But when you have freedom to make your decisions, you choose the worst case. You choose the worst case. Yeah, so this part, a little hard to understand. Let me elaborate a little more. All right. When the given condition can help you make your decision, you use it. All right, so here, let me write. Yeah. So the two, so here, the strategy. So here, let me describe the strategy. Okay, all right. The strategy, there are two parts for the strategy. When the given condition can help you make a decision, you use it. Okay? 2. If you cannot apply the given condition, yeah, so that means you have freedom to choose the result. So then you choose the worst case. Yeah. In this case, so you need, because we target the worst case. We target the worst case. Right? Yeah. So let me show you a few steps. Yeah. So I don't want to give you the whole question, the solution. Yeah, but I show you partial steps. So you complete the remaining part. All right. Yeah. When we start our insertion, right? Yeah. So I just run a few insertion steps. Okay. All right. When we start the first element x1, right? Because we need to follow the order, right? Yeah. Follow the natural order, given order. So, all right. Then insertion. When we insert x2, now you check if the given condition can help you make the decision, right? Yeah. Yes. Yeah. The given condition, because based on given condition, after one comparison, this is the result. Yeah. So you apply the given condition. All right? Yeah. For the next one, next run insertion, sorry, 1. Yeah, so here. X3 insertion, then the given condition, now check. Okay? Yeah. For less than, so you need 2 comparisons, right? So plus 2, right? There are 2 more comparisons. You need to compare x3 with 1, then with x2. Okay? All right. So after 2 more comparisons, you have the order. 2, 3, 1. Right? All right. Okay? All right. Then the next step. So the order becomes x to the 4th insertion. When we consider x to the 4th, now look at it, our strategy, the second part. The given condition cannot help us make the decision. We have freedom, we have the flexibility, we choose the worst case. So we do the maximum number of comparisons. Okay? Yeah. So, yeah. All right. Yeah. So you need 3 more comparisons, right? Yeah. 3 more comparisons. Okay? Yeah. Yeah. So, but the 3 more comparisons, what should be the result after 3 more comparisons? Yeah. So you actually have 2 probabilities, right? 2 cases. All right. So here, yeah. So here in our analysis, we do a little more work. Yeah. But if we can figure out, yeah. So 2 cases. Yeah. One is x4, x2, x3, x1. One is x2, x4, x3, x1. Yeah. Which one is worse? Yeah, because we target the worst case. Now there are 2 cases. We need to choose one of the 2. So which one do you feel it would give us worse? That means we need more comparisons for the sorting. Yeah. More comparison for the sorting. Okay? Yeah. Second position, then you look at later 2 more. So because you push x4 to the right? Then next 2, yeah, because that's with the given information, then you will do fewer number of comparisons, right? So you want to push x4 to the left. Yeah. Right? Then, because in this way, you need to do more comparisons. Yeah? Because you have more elements you need to go through. Think about when you reach x4, you need to go through more elements, right? Yeah. Apply our intuition. That's our intuition. Okay? All right. So that means we should target. Yeah. So we pick this for the worst case. For the worst case. Yeah. Things like that. Okay? Yeah. So here I just do, partial solution. Yeah. So hope to give you the, the main points you need. You complete the remaining half. Okay? Try to grasp the main idea here. Okay? Yeah. So is it good enough, Lauren? After, yeah. Think about it. Yeah, because when you go home, you can, try to understand it better, all these steps.
Yeah, this helps me out because I was doing this right the first time.
Yeah. Yes. That's the main point. Yeah. Okay. Yeah. All right. Yeah. So that's this question. Okay. All right. Another question similar to this one. Yeah. This one. Yeah. You can use the similar idea here. Yeah. The given condition. Only 3, so here. But you need to do things slightly different. All right. So you only have these 3 inversions. Then for all the remaining elements, there is no inversion. That means for all the remaining elements, they are in ascending order. Only these 3 places. Only for these 3 local pairs. See? These 3 elements, 3 local pairs, or better than local, 3 adjacent pairs. Yeah. Because local is still not strong enough. It's not strong enough. 3 adjacent pairs has 3 inversions. Yeah. All right. So then, the remaining elements in ascending order. Yeah. So if we write it ascending order, remaining. So 1x1, x3, x2, x4, x6, x5, x7, x9, x8. That's the given information. Okay? Yeah. Ascending order like this. All right? Yeah. So you recovered the order of the given data explicitly like this. Then you run the insertion sort and count number of comparisons. Okay? So here, everything is certain. Yeah. So when you run insertion sort and do the counting, it is certain. Okay? Yeah. So no freedom, no flexibility, and no worst case. Only one case. Okay? Yeah. So only one case. No flexibility. So only one answer, one possible answer. Yeah. Still run the insertion sort. Yeah. Now, it's very easy. Yeah. So you do not need to make decision. Just keep track of your data closely, step by step. All right? So that's this question. Okay? All right. Yeah. Yeah. Still, check your understanding on the insertion sort details. Yeah. So mainly, you need to understand the data, okay? You know, based on the different states of the data. So you want to see how the algorithm really works. Yeah. So that's the purpose of these two questions. Okay, all right, yeah. Yeah, so that's I want to explain here. Here. And other elements, yeah, definitely there are a few more questions related to the merge sort. So today I don't want to spend too much time, yeah, because today I want to, you know, follow our plan to complete the heap sort. Yeah. And another thing is I want to give you more time so you do the work first. So this weekend, so I hope more students, so you work on the questions, you get some experience, then you can ask me questions. So then next week we have 2 more classes on Monday, Wednesday. So if you really have some questions you want to ask me, so you can use those 2 classes, you know, ask me. So I can give you hints, explanation, things. Yeah. But one more, yeah, because yesterday I checked the email. One student asked me another important question, so I want to explain it today. Yeah. Question number 12, the binary search, the average case, the binary search. Yeah. This question. Yeah. So we have an array with 24 elements. Yeah. So here I use this line segment to represent an ordered array. Yeah. So with 24 elements, 1, 2, the position number, 3, 4. Okay. All right. 5 and so on. Okay. All right. So the right-hand side part. 24, 23, 22, 21, all right, and so on. Okay, all right. Yeah. Yeah. So I want to explain the meaning. Yeah. So what's the right way to understand this question? All right. And the given key appears in the array, and it is between 4th element and the 21st all right, element. Yeah. Inclusive, right? So inclusive. So the key falls into this range. Okay? Yeah. The search key. Yeah. That means the first 3 elements and the last 3 elements will not have any chance to be the search key. All right, so that's first on that. Then, but when we do the analysis, so how do we work on the data? What is the right way to work on the data? Here, I want to explain. The right way to work on the data. Yeah. First, we need to draw the binary tree, right? Yeah. First, we need to draw the binary tree. Corresponding to the binary search. Yeah. But when we draw the binary tree, there is one important point. All right. We need to factor in. So what's that point? Look at so here, no. The information is hidden at the runtime, and you cannot adjust your algorithm based on the information. That means, yeah, so how do we use this understanding? Okay? The use is when you draw binary tree, okay? Yeah. Draw binary tree on the whole array. You should draw on the whole array. Okay? Not just on the partial array. Partial array means between fourth element, 21st element. Yeah? Because some students, it is very, very likely some of the students, yeah, because, you know, the given key falls into that range. So when we draw binary tree, we only draw this part, related part. No, because you cannot modify your algorithm. Okay, so your algorithm already written, it's there, it's fixed. We just apply. We feed the input. The input is the whole array, right? So the input. Yeah. All right. So our data. So the whole array. Our data is the whole array. We cannot cut off the data, right? We need to keep the whole array as our original data. So your binary tree should cover all the elements of the whole array. Okay? Yeah. So that's the first step. All right. The second step. When you count the number of comparisons, for number of all the levels because for different levels in the binary tree, the number of comparisons are different, right? Yeah. So, but when you do this, when you count number of comparisons, actually there is another thing you need to count. Another thing you need to count, and the number of nodes. Okay, and the number of nodes. Yeah, yeah. You add this part. Okay, for all the levels, you need to exclude x1, x2, x3, and x22, 23, 24. Yeah. When you do the the counting, yeah, because when you calculate the average, okay, right? Yeah. Average number of comparison, right? Yeah. You have numerator, denominator, right? Yeah. So the denominator number of nodes in the range. In the range. This range. Okay? Yeah? That's the range. Yeah? Because you have no chance to make your given key hit the left portion and the right portion, right? So these two portions are excluded. So you have no chance to hit those parts. So in your binary tree, you exclude these two parts. You know, cover those nodes. Okay, you do not count. When you do the counting, count the number of nodes each level. You don't count those nodes. Okay, yeah. Only count the nodes in the range. Okay, yeah. Then the numerator, then you know, number of comparisons times number of nodes for all levels. Okay? Yeah. So the range condition impact on your final formula. Okay? Yeah. That's the meaning. Impact the final formula. Yeah. But your binary tree, it should be the whole tree, not a partial tree. Okay? Yeah, when you draw it, yeah. At the beginning, when you draw it, you draw a whole tree. Okay? Then you take out. Yeah, because if you skip, I'm afraid you draw a wrong tree. Right? So why I emphasize you need to draw the whole tree, because some students, before they draw tree, they already exclude the two parts, the two unrelated elements, exclude. Then your binary tree will be shorter, right? Smaller. When you draw, the level will be fewer. You will have fewer levels. Then you mess up. You change all the information. You change all the structure of the binary tree. Here, I ask you, do not change the structure of your binary tree. So you draw a binary tree covering all of your data. Yeah. Think about, because this key, I ask you, you just do one of the search operation, you have this range. But think about, if the next search, your range will be different, right? The next search, yeah, because the range will be different. So that's why we should draw the whole binary tree. Then we can cover all the possibilities. You cannot draw a smaller, shorter binary tree. Then for later binary search operations, out of scope, right? Yeah. So here I only ask you, we only do, you know, the calculation for one binary search operation. Yeah. All right? Yeah. So that's the meaning. Yeah. Yeah, I hope. So this explains the, you know, all the possible questions related to this question. Okay? Yeah, no confusion. Yeah. 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 All right. Yeah. So that's today. So that's much I want to. Yeah. So then for other questions, we still have 2 more classes. We can cover a few more questions. All right. Yeah. Now let's go to heap sort. Yeah. This time we need to do the work. Okay. Yeah. Data part. This time we need to work on the data related to the heap sort. All right. So let me jump to the, so we've complete the structure, right? Yeah. So the next topic, this one. Yeah. Heap property. Yeah. So now we are here, the heap property. Right. Right. Yeah. First, relationship among heap nodes. Yeah. So we need to understand the data distribution in a heap. Yeah. All right. So it's a binary tree stored in an array. Yeah. So, all right. So then, let's look at the details. No. Yeah. So each node we can use its index to identify the location. Yeah. That relationship between two nodes. Yeah. Yeah. All right. Yeah. So actually we did this last time. All right. Yeah. So yeah, we already did last time. That's the definition of parent-child relationship. Yeah. So I think we complete this slide. All right. Yeah. 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 All right. We're here. Yeah. Relation among the heap nodes. Max heap and min heap. Yeah. So here, let me give you the meaning. Max heap and the min heap. Yeah. Max heap property. Yeah. So max heap should follow max heap property. So what's that property? That is A of I, the value of the parent node should be greater or equal to the value of its left child node, and also greater or equal to the value of its right child node. Yeah, so very natural. That's the max heap. Yeah. If, and this property holds everywhere in this heap. Okay? Yeah. Everywhere. Yeah. Then we can call this is a max heap. This data structure is a max heap. Similarly, we can define a min heap property, right? Yeah, min heap property just the opposite. The directions of the inequality is just opposite. So we have a min heap. Yeah, yeah, and we only need to look at one of the two cases. Yeah. So in this class, we just study the max heap property. Okay. Yeah. All right. Next, now we need to. Yeah. So here I want to show you a max heap example. Yeah. So we want to see a concrete example. Yeah. So look at this one. Now we need to check. Yeah. So how to see it is a max heap. Yeah. So let me show you. Yeah. So when we check, all right. First, you can see these numbers. The number inside circle, that's the value of this element. All right? So the numbers, that's the index numbers. 1, 2, 3. Yeah. So these are the index numbers. All right? Yeah. So then the values. But when we check max heap, we need to check all the local triangles. One is here. Yeah. So this local triangle, yeah, although no right child, yeah, but still we can check the value, right? Parent 7 greater than 1. So then another local triangle, yeah, so 8 greater than 2 and 4. Yeah, so follows a max heap property. This local triangle 10 greater than 9 and 3. This local triangle 14 greater than 8 and 7. Then the last local triangle 16 greater than 14 and 10. Yeah. Then we can say it is a max heap. Yeah. Simple example. Yeah. All right. Yeah. Yeah. Then, yeah, when we store, yeah, because that tree, it's an imaginary binary tree, but in our main memory, we need to store the whole heap max heap in an underlying array. So the way we store 16 here, there, 2 child nodes, 14, 10, yeah, 2 child nodes. Yeah. So the index relationship, left child double the index, right? Right child double then plus 1. So 3. Yeah. Similarly, for node 14, it's 2 child nodes, yeah, 8 and 7, index, left child double the index number, right child double, then plus 1. See? Yeah. Very well organized, right? Yeah. The next node, the 2 child nodes, yeah, left child double the index, right child double, then plus 1. So, perfect fit, right? Yeah. So another parent child like this, double left child, right child, double plus 1. Okay? All right. The last one, double. Okay? Yeah. See? Yeah. So works so well. Yeah. No hole inside, right? All these locations are used, yeah, except the first one. Yeah, first one. Yeah. So we leave it out, so it's, not big loss, right? Yeah, very little loss. Yeah. All right. Yeah. And in this way, think about, we do not need to use linked list. No concrete links needed. No concrete links needed. See? Yeah. So that's very convenient. Yeah. Yeah. Because when we need to manipulate the links, too much work, too messy, right? Yeah. So here, yeah. Yeah. So simple. Yeah. All right. After that, now we feel comfortable. We can use an ordinary array to store any max heap. Yeah. Question? Yeah. Relationship triangle, yeah, based on our max heap property, the value of the parent node must be greater or equal to the value of each of its child nodes. Yeah. So that's why, yeah, but then we need to check all the possible local triangles. Usually we use the bottom-up way to check. We want to follow some natural order. We don't want to miss any local triangle. So when we start from the bottom. Then from right to left. Okay? So we go from right to left. Yeah. Rightmost local triangle at the bottom. Then the next one. Okay? After we complete the bottom level, then we move one level higher, starting from the rightmost local triangle. Okay? Then check condition. Okay? Yeah, we check carefully. Yeah. So then, follow the order. So bottom up way. Then in this way, we can make sure we cover all the local triangles. Yeah. That idea. Okay? Yeah. Very simple. Yeah. Yeah. Then when you write a code, you need to implement in this way. Yeah. So you need to implement in this way. Okay? Yeah. Keep track of your data. Yeah. In this order. Yeah. Yeah. So that's what we call advanced data structure. Yeah. Because you need to do more work. Related to data structure, you need to do more work. Like this. Okay? Yeah.
Can you explain to me why the 2 and the 4 is different? Like if we're looking at 14 and 17, that I have 2, 4, but the bigger number's not on the left. So.
Bigger number. Yeah. Oh.
No, why 2 is in the 8th position instead of being in the 9th position? Just says the numbers inside the 8th.
No, here, right?
Yeah, like
2.
Like why is 2 in the 8th position and not in the 9th position? If I compare it to
So here it's not in order, right? 2 appears earlier than. Because Yeah, good. The question is, the order of the values between left child and right child, no requirement. Yeah. Any order. Yeah. So we do not require, a value of left child greater than a value of right child. No, we do not require that. That's why, so the numbers, it's not in order. Okay? Not necessary.
So
yeah.
7 could have been swapped.
Yeah, could swap. Yeah, so these two numbers we can swap. Still, no violation of the max heap property. Yeah, yeah. So that, yeah. Because our max heap property does not require that. Okay, yeah. So that's the reason. All right. So next, maintaining the heap property. Yeah, we need to consider that. Maintaining heap property then means sometimes when you do operation, you may violate the heap property. Yeah, because you need to do operation, insertion, deletion, right? Yeah. Remember, we use this heap data structure to manage the dynamic data. Yeah. When you work on the dynamic data, you need to insert a node or delete a node, right? When you do that, the max heap property could be violated. So you need to fix it. Yeah. So that step, so we call it maintaining the heap property. Yeah. All right. So here I want to show you where the heap property or max heap property is violated due to some operations. We need to run some fixing operation to recover the max heap property. Yeah. So that's what we need to do. Okay. Yeah. So here, let me work on the local triangle to show you the logic to recover the max heap property. All right. Analysis here. Yeah. Violation occurs locally. Yeah. So, yeah. Because when you check max heap property, suddenly you discover there is a violation. Yeah. So the two inequalities do not work. Then you need to run some code, logic, to recover the max heap property by swapping, right? You can swap the values of the nodes. Yeah. All right. Yeah. So let's look at the local fixing operations. Yeah. So we want to fix locally. Okay. Yeah. Yeah. So this within this local triangle. Yeah. For the global, after we fix the local triangle violation, then we can look at the global issue, right? Yeah. So let's do local first, then global. Check for violation globally. Yeah. So later we need to make sure no violation occurs globally later. Yeah. Yeah. All right. Local heapify operation. Yeah. So this we call a local heapify operation. Yeah. So it's a recursion approach. All right. Yeah. So in this, so let's look at the pseudocode. If A of I less than A of 2I, it's a violation, right? Yeah. So this inequality tells us there is a violation in this local triangle. All right. Then we need to prepare for the swap operation. We do not do swap immediately. So here, think about the logic. Yeah. Because although this fixing operation is very simple, but we want to do it carefully and in the most efficient way. What is the most efficient way? We want to minimize the number of swap operations. Okay? If you swap more than necessary, then you waste your computing resource, right? We want to save our computing resource. So how to save computing resource? We want to do the minimum number of swap operations to save. Yeah. All right. So here, after we detect there is one violation between the parent node and its left child node, So we use a temporary variable called the largest. We store the index of its left child node to I. So we store the index number without doing the swap. We delay the swap. You can understand this. We delay the swap because the swap may not be necessary. After we delay, we can reduce the number of swaps. There is a possibility to reduce the number of swaps. All right, so let's just store the information without swapping. Else that means no violation, right? Else means the value of parent node is greater or equal to the value of its left child node. No violation, then our largest temporary variable, we store the index of parent node, I. Yeah, no violation, okay? Yeah, all right. So, but our largest temporary variable stores the index of the larger value of these two nodes between parent and the left child. Next round, we consider the right value of the right child node. We compare A of the largest. If A of largest less than A of 2i plus 1, then another possible violation, right? Yeah. So we detect another case for the violation. Then we need to update the value of this largest variable, right? This time, the largest equals 2i plus 1. Okay? Yeah. All right. So then, we need to do the last round, we need to do the swap operation. Okay? We need to check if a swap is really needed. If the largest is not equal to I, then a swap is needed, right? Yeah. If the largest equals I, no swap is needed, right? No violation. So the last round, first we need to make sure there is a violation. There is really a violation detected. Okay? All right. Oh, yeah, detected. Yeah. Then we do the swap. Yeah. Swap A of largest and A of I. Yeah. A of I, the parent, the value of the parent node. Yeah. A of largest, one of its child nodes, either the left child node or the right child node. Yeah. In this way, we only need to do one swap. We never need to do two swaps, right? Yeah. Yeah. If you do swap, when you detect a violation, you do swap immediately, then you may need to do two swaps, right? You may need to do two swaps. So in this way, if we delay the swap, then we always need to do one swap operation. So we can save. Yeah. Yeah. Because swap operation, sometimes you may need a little more time. You may need more time. When you call swap operation, basically you copy data, right? Copy data from this location to that location, then to a temporary location. Yeah. When you do the data copy, think about when you do the data copy, it takes time, and especially sometimes some node may carry large amount of data. It's possible. Yeah. Because one node, you may associate a block of data in one node, right? Yeah. So block of data in one node, then you need to copy the whole block data from one location to another location. It takes time. Okay? So you don't want to do more than necessary data copy operations. Yeah. That's the main point. All right. Now we complete this local heapify operation. Next, let's look at a heap example. 8.4 heap example. So this time we want to, so run max heapify. So what's the max? Yeah. So we detect one violation. So we want to run max heapify operation. Max heapify operation to fix it, to recover the max heap. Here, in this diagram, I use gray color to color the node that tells us there is a violation occurs at this point. Yeah. So the violation, you can see, starting from this gray node, there is a violation here. Okay? Yeah. So we need to run the max heapify operation to recover the max heap property in this location. All right. So then, so we just run other, max heapify operation. Then we need to swap the values of these two nodes, right? Yeah, because the largest temporary variable should store the index of this node. So after the swap, so we move the gray node down. Yeah, so this gray node, we can call it a dirty node. Now, it is dirty because there is a violation at this location. Yeah, so it's a dirty node. But we move this node down to the bottom. Yeah, but because it is dirty, we still need to check the violation starting with this dirty node. And keep track of the dirty node. Yeah. So here the strategy. Our current strategy is we want to keep track of the dirty node. And we want to make it clean. Yeah. This dirty node, we want to, follow this dirty node all the way down to the bottom until it is clean. Yeah. If it is clean, then we stop. Yeah. All right, so this time, another dirty triangle, we need to fix it. That means we need to do a swap operation between these two nodes, right? These two nodes, okay? All right. Yeah. After that swap operation, then the original dirty node hit the bottom, then it cannot be dirty anymore, right? Yeah. Because if a node hit the bottom, there is no chance to have a violation, right? Around this node. Yeah, it's already at the bottom. So no chance to make a violation around this node. Yeah. Then it becomes clean. When it hits the bottom, it becomes clean. Yeah. Okay? Yeah. All right. So then, because every time we find one violation at one point, so we need to keep track of that dirty node all the way down to the bottom. Yeah. So we have a, max heapify operation. Yeah. All right. Next, I want to show you an example called building a heap. Yeah. Building a max heap. Yeah, here. All right? Because when we start with an arbitrary array, right? Yeah. Arbitrary array, in general, it is not a max heap. Yeah. Arbitrary. Now we need to run some operations to make it a max heap. Yeah. So we call it, this is a build a heap process. We need to run that process. Build a heap. Yeah. Let me show you an example. So how to build a heap here. Yeah. All right. Yeah. So when we start, this is the given array. So definitely it's not a max heap. Yeah. So when we start arbitrary given data. All right. When we start, first let's arrange the data based on our heap structure. Yeah. Following the natural order, okay? Yeah. So the first node we put at the root, then the next level we use the elements following the given order. Okay? Yeah. So we do not do anything. We just arrange them in that order. All right. Then Now we need to, because here you can see, we need to, in order to, so here the idea, how to build a max heap. First, we need to detect max heap violation everywhere in this heap, right? Yeah, because we may have a lot of violations. So we need to detect and fix the violations everywhere in this heap. Yeah. All right. When we do the detection and the fixing operations, so the order we follow, we use the bottom-up approach. And the bottom, when we start from bottom, we check the rightmost triangle. Okay? No violation, right? So we move to the next local triangle. And in this place, we find a violation. We find a violation here. So we need to fix it. Okay? So we run the max heapify operation. Yeah. All right. So to fix this one, after we fix this local triangle, we move to the next local triangle. Yeah. So because we finished the bottom level, we move to the next level higher, and we find another violation. Yeah. Then we run the max heapify operation to fix it. Okay? Yeah. By a swap operation between these two nodes. All right. After that, we move to the next local triangle. Okay? So we detect another violation. This time we need to do another swap. Okay? But after the swap, think about it. After the swap, so when one is here, we need another swap, right? Yeah? Because you need to keep track of the dirty node until it hits the bottom to complete the max heapify operation with respect to the dirty node. Yeah. All right. Then next we move to another local triangle, another violation. Yeah. So swap between the two. So move down 4, but another, we need to do another swap between these two nodes and another between. Okay. Yeah. So you need to do 3 swap operations. Yeah. So after first swap operation, the dirty node, you get a dirty node in this location. So another swap operation, the dirty node get that location. Then the last one, after last one, yeah. So you'll fix it. After that, because you already reached the top, you already complete the processing of the last local triangle. So you fix all the possible violations. Yeah. Following this bottom-up order from right to left, and the bottom up, this order, then you can catch all the violations.
For the last triangle, looking at it was for 16, 10.
Yeah.
You move the 10 first and then the 16, because you're always starting from the right side. But when you just look at each of the elements and compare whatever's the largest. That one.
Only, so the last, so we always swap with the largest value, 14. Not with, because, after that, so let's show the previous one. 4, you don't want to swap between 4 and 10, right? Yes, yeah. Based on our code, the largest, we catch the largest, the node containing the largest value. Right. Yes, yeah. So So otherwise, you won't get the best arrangement. Yeah. All right. Yeah. So after that, okay, here. After that, we build a max heap. Okay. Yeah. So for the given triangle, the given array, we can build a max heap. After we get a max heap, then we are ready to run the heap sort. Okay? So why we do the max heap? Yeah, because this friendly data structure, we want a friendly data structure. Yeah, we can take advantage of its special properties to complete the heap sort. Okay? All right. Yeah. Yeah. 8.5, heap node in each level. Yeah. So the next step, next topic. Yeah. So today we cannot do it. Yeah. So here I just say something. Yeah. Give you a short introduction for the next topic, 8.5. So for the 8.5, we want to, because after we complete the heap sort, we need to see how many comparisons we use in this heap sort. We need to do analysis. So when you do analysis, you need to count the number of heap nodes in each level. Okay? Yeah. Count the number of heap nodes in each level. Yeah? Because when you do the max heapify operation, when the dirty node in different levels, the number of comparisons or swap operations. Yeah. So we still use comparisons. Okay? Comparisons including swap operations. That number depends on the level number, right? Yeah. The level, high, low. So we need to get more information about the level and the node number, each level. Yeah. But, so here, another thing. So in our next class, is the meaning of level. Yeah. So what's the meaning, exact meaning of levels in a heap? Yeah, so here, the definition of this level meaning could be different. So when people talk about the level number, so there are several different understandings. So first we need to clarify what's the exact meaning of the level number. It's quite different. So next time I will define this level number. All right, so let's stop right here. So we need another class, but because we spent quite some time in our homework assignment. So next, we will do the similar way. We spend half of the class on the hints of the homework assignment. Then the remaining half, we complete this whole heap sort. We hope. So remaining still a lot of things. So I hope we can complete. All right, that's it.